So, here's Perspec Composer. It's a UML-based GUI that allows building scenarios and use cases and opening coverage and review coverage and even do debug. We're going to just demonstrate today the scenario creation from here. So here's the gallery. We shrink everything. Here is the gallery of the components and their associated actions. And I can select those and create combination of those with control flow, with data flow, and create my own use cases and scenario. And let's start with what we used in Accellera tutorial. I'm just going to take the loopback test. And what is the loopback test? We're actually reading and using the UART and at the same time copying whatever we received into the memory with the DMA Q to mem action. And after that, we start two parallel activities of taking the same memory buffer by the DMA, copying it to the FIFO, and then sending it back again. So this is the loopback approach. Now there's many parameters here. Look at the code of this, right? Here, activity loopback, parallel, do read in, do Q to mem from the DMA, parallel, do mem to Q of the DMA, and do write out by the UART. Now there's many parameters here that I didn't set. What's the buffer size that I'm going to copy? What's the data size? What memory location I'm going to copy into which DMA channel is going to be in the loop. So if I click the solve button, Perspec basically show us the randomized scenario in the specific details. So this is a UML activity diagram, fairly intuitive. Start, end, parallel bar. So we start, and then we parallel, we do the UART read in and the DMA Q to mem, which is going to result this data buffer. And then we're going to read that data buffer. Again, in parallel, DMA is going to take that data, pass it to the UART to be transmitted. I can see exactly which DMA channel was selected. This is ID 0 in this case. And let's see, yeah, we got the same DMA channel selected again, which makes sense because these two actions are not active at the same time. So here's the solution that we got. I can look just on the scheduling of things, and you can see the two parallel activities followed by another two parallel activities, or just on the data passing. This is what we see here. Okay, let's create something on our own. We're going to start in something with something less sophisticated. I just want to get a write out activity. I don't care how the information got to the memory. I just want to get a write out. So this is a goal-based approach. The tool will find a way to accommodate my request. By the way, I can, if I want, put constraints on these attributes. What buffer size do I want to get? What data size do I want to get? So, but I'm going to leave it with that. I'm just going to click the solve button, and we'll see some of the key capabilities and concepts of PSS right away. So here's the write out. This is what we explicitly ask for. These actions were introduced by the tool knowing the model introduced to accommodate this request and eventually achieve a legal scenario. Here's a legal scenario. Start point. Some initialization need to take place, and one of the cores was randomized. You can see that core number 2 was randomized to create a write data to initialize this data buffer, and then our mem to Q transfer of the DMA pick that information and send it to be transmitted. And then we finalize, and that is the end of this scenario. Very straightforward. Let's do use some of the operators to get more control flow. So I'm just going to take this and I'm going to do repetitions. So repeat this write out. And I'm going to do solve. Here it is. We got something a little bit more sophisticated now. So you can see these are the three write outs that we've asked for, and you see the mem to Q transfer that were added to accommodate our request, our scenario in here. Okay, so by the way, this is gen time, right? We've solved 3 times, create 3 instances of the write out. What if I want to support post-silicon environments? I want to go to millions, right? So no problem. You can change the attribute to be loop in runtime in the generated code. And I can change this to be 1,000 if I wish. And click the solve. And we're getting now a different solution. And you can see that we have the loop in here that was created. Let me just take it here. So we're basically have a loop of 1,000 of this entire scenario. This is actually a loop that is going to be generated in C or in System Verilog, whatever you want, but that's what we're going to get. So we'll see more of that as we continue. Of course, this supports also runtime select and if, etc., but that's maybe in the next video. Let's make our solution a little bit more complicated. I'm going to create a solution like that. Let's say I want to stress the interconnect and I want to do some memory buffer initialization. Then I'm going to copy it all over my memories. And then I'm going to do a self-checking at the end. How do I achieve something like that? Okay, so I'm going to use basically a macro, a GUI macro that we have. Instead of dragging 3 times, I can do replicate, dragging into a schedule, right? So here's a replicate, and let's use our memory initialization. I'm going to ask one of the cores. I'm not going to say which one, but one of the cores. And I'm going to do the replicate 3 times. So let's initialize 3 buffers. And then let's do this. I'm going to do another replicate. And this time I'm going to select to do either a copy by one of the cores or do a DMA transfer. So select one of these. And then we want to finish with check that the CPU can do. So here's the check of the CPU, and I need to put that in a replicate also because I want to check these buffers. So here they are. Let's check our 3 buffers, and to make this more interesting, this is going to be 22 times this selection. So here we are. Much more sophisticated right now. And let me again, you can see that we got lots of traffic. I can put coloring here to make sense out of it. So let me just color it. There's various coloring and you can define your own, but this allows us to see very nicely what's going on. So look at this. We have the 3 initialization at the beginning, then we see the nice mix of the copy and the DMA transfers, and then we have the checking at the end. So I can look just on the timing, and this is what's going on. You can see the parallel activity, but I can look at the chains and look at that. Initialization, copies with a mix of copy, core copy and transfer, and the finish at the end. Now each one of these blocks is translated into code. Could be C code, could be backdoor checking, could be whatever you want. I'm going to cover that probably in the next video of how is it that we achieve the realization. So this is one more interesting thing. Let's demonstrate a little bit resources and what PSS can do for resources. I'm going to take 3 DMA transfers, and let's take 2 of them and make them in parallel to each other. So I'm going to take this and just copy it into a DMA transfer. Look how quickly I can achieve parallel 2 activities with another activity. Here's the scenario. Let's look at the timing and you see what's going on here. This is the timing. Now notice if I click solve, there's always 2 at the same time and then the 3rd one. And if I look at it, look at details, you will see that actually since these are in parallel, the resources are distributed 0 and 1 in a legal way. Now, if I drag the third one into my parallel block, remember we only have two, I will get a contradiction. And you will see that we're trying to basically utilize two resources with three requests. That is impossible. Now, this is simplified, right? I just drag and overutilize the resources that I have. But this is what's happened when you create system level scenario. You create something and you need to take into account address alignment and availability of resource and configuration and operation modes and all these things. And this is exactly the kind of challenges that PSS is very powerful in solving. Okay, so this is kind of concluding what I want to show you. We can cover much more in upcoming videos, and let's move forward with the session.